Here for Singularity discussion, Singularity 2, Jim Larus, Galen, and two new faces, Manuel Fahndrich.
David Tarditi.
Outstanding. So let's talk about Singularity. Last time we gave a broad overview of what it is. Maybe we can touch on that again, just so people know what Singularity is, why it's being done.
So Singularity is a project we started 2 years ago inside Microsoft Research. And we started with a sort of simple question, which was, what would software look like if you made dependability your main goal instead of, typically performance is an important goal for most people writing software. So we said, if we can de-emphasize performance and really try to make software more dependable, more reliable, more robust, more secure, how do we go about doing this? And we had a lot of technology available to us inside Microsoft Research. We've done a lot of work on languages, we've done a lot of work on compilers, we've done a lot of work on program analysis tools, we've done some work on operating systems as well. And we thought, okay, let's go and sort of take this and take into account the fact that there are a lot of technologies available. Let's see how they will change the entire software stack from the hardware on up. And so that's where Singularity got started from. And we made a number of design choices that look quite different than operating systems today. We basically decided that we were only going to use safe programming language and an extension to C# throughout the entire system, from the hardware on up through the applications. And that had lots of consequences in terms of the structure of the system, the architecture of the operating system. We also decided that verification was extremely important to us. We would like to be able to apply tools to mechanically and systematically check the properties of the system. So we designed the system to encourage that and make it more possible than existing systems. So that's sort of, where we got started with Singularity. And, as we dive into the details and talk about it, we can explain sort of how a choice in one area actually has repercussions in lots of areas. And that's one of the really interesting parts of this project is that, we started by making a few changes to the system, and the end product looked totally different than what most people think of as an operating system these days. But we can point to the parts and explain why we made these choices and how we got to where we are today based on the decisions we made and why we think this is probably a good way for software to evolve in the future.
Well,
You can now disagree.
I like dumbfounded again, don't I? This is actually a normal occurrence in the meetings. They look at me and I've got nothing reasonable and intelligent to say. Actually, I think a really good. So, I think one of the important questions that came up a lot from people from the previous video that we did was questions about how do we run managed code? How do we take managed code all the way to the bottom of the stack?
Yes.
And actually, I'm going to turn it over to David. So David runs the compiler group, part of Singularity. And I guess one of the things we should mention here too, so you're going to see 4 faces, and you've seen 2 before, and this is actually out of roughly 12 people that are working full-time every day on Singularity kind of thing, and then roughly another 20 people at Microsoft Research that contribute in some way or another. And so, while you've seen Jim and I's lovely faces, they're actually more handsome and intelligent people on the project, and let's turn to some of them now.
We keep them in the back row.
Anyway,
So
David,
so
about the part.
I manage the Advanced Compiler Technology Group, and we've actually been working on compilation of we've actually been working on compilation of managed code to native code for a long time now. So this stuff actually goes back almost 8 years, and the Bartok compiler goes back 4 years. And so the goal was, basically, we were already on this idea of trying to get people to write programs in safe code. And the idea being that if you write the programs in safe code, certain kinds of errors go away, and in general, it makes it possible to prove properties about the system. For example, it's actually possible, if you're writing in safe code, to prove properties about the machine code that's spit out by the compiler. You can actually generate this typed assembly language stuff that was talked about before. And if you're not working with a safe language, you can just, I would say you can't do it, but it's much more difficult, would be the best way to put it. So we were working on Bartok for a while before these guys came along and said, we want to do an OS on top of this. We actually were worried about like I said, the problem of taking safe code and compiling it down to native executable code. So our system has a very different flavor than most just-in-time compiler systems. We actually use a traditional ahead-of-time compiler, and this is analogous to what you might have done before something like Java came along, where you had a language like Modula 2 or Modula 3 that were safe languages. You would compile them down to standalone.
C++.
Okay.
There's a subset that's safe, though,
Yeah.
and you could work with that subset. Pascal might be an
And
example.
can I just say, so what you're saying is you took away the intermediate step of IL. So you're going
Oh,
straight
no,
to
no.
Okay, let's talk about that. 'Cause,
So what happens is you compile your program, just like you do now, down to an executable file that contains IL in it. Okay. Then you point our compiler at it. Our compiler reads in all of the IL. In fact, it reads in all of the executables and the DLLs that make up your program. It reads in all the IL, and then it compiles the IL down to native machine code. So you can think of this is something that the just-in-time compiler does, but it's all hidden from you, so this isn't exposed to you. So we actually read in all the MSIL, and out comes a new executable that's x86 machine code. That's how it works. Now, what we do is we actually wrote the entire runtime system in managed code also. So in fact, our garbage collector, our type test lookup, our thread management, the whole core of the runtime system is written in managed code. Now, some parts of it can't be written in safe code because it's an open research problem, like garbage collectors. But it's still written in managed code. So our compiler can read in the entire runtime system that's needed for the rest of the code to run. It compiles that down to native x86 code. You link the whole thing together using the regular Windows linker, and you can run this. And in fact, the compiler actually operates in a couple different modes. One mode is whole program compilation, so we can read in everything, including the runtime system, generate a specialized version of the runtime system with the sort of runtime system compiled in, and out you get this native executable that runs. And that's what we actually run on top of Singularity. So this is how you need this kind of approach frankly, if you're going to try to bootstrap a kernel or anything like that. So we've actually got hooks in here for interoperating with some of the legacy code that you need when a kernel boots. But you can look at it this way. This is just the same thing that you would do with C code, is you compile your C code, you get a native executable, you link it with some libraries, and that's what you run. And the libraries themselves are written in C code. So if you look at this in our world, everything's written in this extension of C#. So you compile the code using C#. You get some object files out. You compile the libraries that are written in C# also, and then you link it all together and it runs. So this is actually a sort of back to the future approach for compiling safe languages. But the flexibility is that, if you're trying to write a device driver or anything else like that, you can't really have a just-in-time compiler kick off in the middle of booting the kernel. You could, but I don't recommend it.
It would be very challenging. I wanted to point out, so David mentioned about, compiling the garbage collector, for example, in C#. And it is just like C. If you think about if you had your C program that you were writing, and you'd do memory allocation with malloc and free, and malloc and free are always just C code. They just know how to reason about memory, and the garbage collector is very similar. It's just C# code. It's unsafe, but it just
Now let's talk about unsafe C# code. What do you mean by that?
So
we think about verifiability, type safety.
yeah. Okay, so from a programmer's perspective, I'm using unsafe C code or C# code. With I can literally use pointers. Okay,
Pointers in the sense of C pointers,
Yeah.
not references in C#, which are strongly typed, where either the compiler at compile time or the runtime system at runtime makes sure that you know exactly what you're pointing to at all times.
So you're literally using
like an
unsafe
address.
block.
Yeah, and the syntax is literally the C or C++ syntax pointers. You have a star, and you can cast things from pointers to floats to
anything.
Yeah, to anything.
This is a standard part of the language too, right? This isn't something we added to C#, right? It's there. You basically go and
for interop.
Yeah, you go and stick unsafe around your code. You've got to sort of, it's like a red badge you got to wear.
Point though, which is that when you run a Singularity application, in fact, when you run a Singularity application, you can't actually write unsafe code for your Singularity application. The only place where the unsafe code is in, what's that? Yeah, the only place where the unsafe code is in is in the runtime system. And we're striving pretty hard in our research agenda to eliminate or reduce that amount of unsafe code to be as small as possible. And now, Galen, you had some interesting numbers about the percentage of code that was safe versus unsafe.
Right.
Um,
Why do I feel like he's got marketing experience? And now, yeah,
well, I think those numbers are great. That's why I want you to talk about them.
So, in the current Singularity kernel, okay, this is all. If you take all the files in the Singularity microkernel, approximately 2% of the files right now are assembly code. Okay, and so this is, I think we mentioned this already. These are the places where, in a traditional operating system, you'd have assembly. Context switch code, thread, the very low end of the thread startup and termination code, interrupt handling code, some exception handling, things like that. Okay, so that's about 2% of the code is assembly. About think about this. About 3% of the code is C++ code. Okay, and the C++, we have a little bit of C++ in the exception handling code. There's a little bit of it for tracing, for some debugging tracing. The debugger stub is actually written in C++. So we can use, it's called, I don't know what it's called in the outside world, but internally we call it WinBag, the Windows kernel debugger that they use for debugging kernels.
That's out.
So we use it for debugging the Singularity kernel. The stub that knows how to talk to that is C++.
In fact, just to add to that point, in fact, the code that comes out of Bartok, we actually emit code that looks like it was produced by a C++ compiler. So it actually has the same PDB, it is the same PDB format that Microsoft has, and it uses the same line number information. So you can literally step through the C# code using the C++ debugger, or using, you could use the source level C++ debugger, or you can use the kernel C++ debugger.
Great.
And then about 17-18% of the code is in current Singularity code base is unsafe C#. Okay, actually the way I would describe this, to be very precise, we have 18% of the files, someplace in the file have unsafe C# code. Okay, and then the remaining roughly 77% of the kernel is safe C# code.
Meaning not wrapped in unsafe
Yeah,
block. Now,
there's
for the
no-
unsafe stuff, I would only ask, why didn't you just use C++? Why would you use unsafe C#?
Well,
Why not just use native code?
so there's a couple of reasons.
Okay.
One of them is what you'll find is a lot of the, so this is, I said 18% of the files have unsafe code, okay? Actually, if you look in there, there's typically aren't very many lines that are actually unsafe.
Okay.
It's like you'll do a bunch of bookkeeping, and then at some point you say, okay, I actually have to touch this piece of memory raw in order to do something, okay? For example, with the page tables. So when we talk about manipulating, setting up the hardware for page management, or the exception, actually exception's not a good one. The threading code is another good case of this, where we can allocate the object that we're going to use for a stack, we can allocate all the memory, and then at some point we actually have to go in and manipulate something in a way, a function pointer, for example, which isn't something you can do natively in C#. Okay, and so you really want to write those in C# as much as you can for a couple of reasons. One of them is every place around that you can rely on safety, you want to rely on safety. Another one is David's compiler recognizes the C#, and so it can optimize it along with the rest of the program, okay? Whereas the C++, it has to treat as just kind of this opaque code that it can't do anything about. Very similar to the way that, say, a C++ compiler treats assembly. It just can't do anything with it. It just says, okay, I'm not going there. But this,
to bring up this point, so what you see in Java systems, for example, are that people have got a C++ implementation of the core runtime system, and then they've got all their libraries written in Java. And one of the problems that you run into when you're a compiler is you can't actually assume, particularly because you didn't compile it, how that C++ code is behaving. And so it creates an interop boundary between the C++ code and the C# code. And that, at the very least, causes and hinders optimization. And at the worst, it causes your compiler to really give up. And not to mention, it also introduces marshalling and things like that that don't really need to be there. So you know, in theory, you could actually write the code in safe C++, for example, and convert it to MSIL and feed it in. We could have gone that approach, but in practice, it's just simpler to have everything in one source file, not have to worry about sort of these interop issues.
Fantastic.
I think one more thing you should really also focus on is the fact that these unsafe pieces of code are not, we don't want to sort of randomly sprinkle them throughout. And you said 70% of files is true, and that's for the kernel, but if you look at any particular process, I mean, there's really just the runtime, which a normal application writer is not going to touch, and all the code that he's writing on top of that doesn't use unsafe, and we of course could check that's the case, right? So I think that needs to be said, because otherwise the whole point of safe verifiable code is sort of moot. But we really try to focus the unsafe part on just where it matters and keep it away as much from the general application development.
There's also another thing people don't sometimes realize is that when we use unsafe code within inside the body of a method, we can provide a safe abstraction. So we can literally sort of wrap the unsafe code in a way in which it can be called from safe code and not violate the safety of the code. So one example we do with this is that the device drivers have to be able to access the physical memory that is literally the connection to the device itself. And so we give them an object which has unsafe code in it that literally accesses hardware memory locations, which is not a safe thing to do in general. But we wrap it in an abstraction, and we do the checking to make sure that the abstraction is safe and can be called from safe code. And so that's one of the sort of ways in which you build a safe system on top of this unsafe foundation. And you don't want to use unsafe code all over the place, but there are places where you have to have it. And as quickly as possible, you turn it into a safe abstraction so that you can use it from general safe code in C# code.
I think in one sense, sort of unfortunate that it has to be called unsafe, because that implies by writing it, it means that you're doing something. It means that potentially something bad can happen, and that you're actually in control of memory. There's no garbage collector, no verifiability, but call it unsafe. Arguably, it is unsafe.
It is unsafe. There are a lot of bad things. I mean, if you're careless in that code, you can, destroy the memory invariants and crash the system very easily. I mean, the garbage collector does depend on a lot of things staying the way it is. With one bad pointer, you can quite easily corrupt the memory system. So, it is. I think unsafe is actually a good warning to you that you should think twice.
It's unsafe, not uncorrect. Hopefully, it's not uncorrect.
That's a good distinction.
Right. I mean, I think in some sense, unsafe meaning it's not easy to verify that it's safe. In particular, not using the standard way that we do verification of C# or IL. And so you need a lot more complicated ways to verify that code is safe. But that doesn't mean, as you said, that it's incorrect. So that's, I think, down the road that we'd really like to push on what we can verify and try to verify even such parts.
We actually have a path for that in terms of some of the spec sharp stuff.
That's right.
We have the way you can annotate the code with pre and post conditions. So you can actually give the system enough information to actually check the safety of some of this unsafe code. This is an open research problem to do this kind of stuff, but it's our general goal. I mean, I think your observation is right on target, and it's our general goal to try to think about, well, how could you actually turn this into something where you can check the property of this system? So, for example, if you're relying on unsafe code because array balance checks and you don't want to pay the cost, well, generally that's something that you actually as a programmer have some idea in your mind about why it's okay to do this. And the key problem is letting people actually express it in the program so that we could check this. And so down the road, we are looking at ways to extend the language so that we could express more. And there's one thing that I can talk about where it's a research result really at this point, but we actually have the ability in our system to be able to take parts of the system like the type test code, and we actually know how to verify the safety of the type test code. This was the Popple paper. So we actually have in mind a richer type system that would actually let us verify the safety of parts of the runtime system. So even though in the Java world, most of the runtime system is written in this sort of unsafe code, or it's written in C++ or some variant of Java without safety, you could actually take parts of the runtime system and move them from being something that you have to trust, that you just trust somebody got it right, to be something that's verified by the rest of the system that is in fact correct.
And that doesn't mean necessarily that you understand what the code is going to do. I mean, there's a
No, it just
difference,
means
right?
that, for example, the code won't corrupt memory, for example. So it's not like when I said correct, I should be careful about that. It really means there are certain properties we know that hold true for this code, but in general, showing the correctness of code is a very hard thing to do.
Sure, that's right. So, I mean, there's a good term for this. I mean, I don't think we mentioned before, it's what's called a trusted runtime, so, or in general, trusted code. So the code that we don't verify for correctness because of various reasons that we call unsafe, we usually call it trusted code, right? So we trust that somebody by hand or whatever made sure that it's not going to do something bad, right? And the rest of the code is the verified code, or the verified for maybe memory safety or type safety. And so what we're really trying to do is reduce this trusted computing base, right, by making either the type system more general so that it can handle more parts of it, and overall over time we want to reduce that as much as we can.
Fantastic.
Yeah, so all the code in the system is either verified, it's safe and verifiable, or it's trusted. And I guess we should, the punchline that we kind of missed is, yeah, 23% of our system has 23% of the files in our system have unsafe code, but 100% of the files in Windows have unsafe code, and 100% of the files in Linux or BSD or any of these other systems have unsafe codes. So yeah, we didn't get to 100%, but gee, we got to 77%.
So pretty, and I can write, and if I were to write a driver for Singularity, I'd write it in C#.
Yes.
Right.
Yes.
In fact, that's all you could write in. We
Yes.
wouldn't let you write it in unsafe code.
Okay.
So, when we say unsafe code, it's in the kernel. It's the code or the language runtime system. It's the code written by Galen or David's group. And we don't expect that the other people on the system are going to need to do that. And if we run into situations where they do, we go and figure out the abstractions that the system should provide.
One point I'd like to make, we actually, well, I guess we have to use C# at this point, but in general, really anything that would compile down to verifiable MSIL would work fine. So if you C++, for example, is this new /pure switch or /CRR switch. And so you can compile C++ down to verifiable MSIL. That would actually work fine in our system. So it's not just C#, it's really anything where you can actually express in some mechanical way the safety of the code.
Could we do VB?
I think we probably could.
So we could,
But I haven't tried it, so.
Written in VB, the first one in the world. That would be amazing.
There are certain features of VB that would cause problems, I think. So some of the more dynamic features of VB might cause us a bit of a headache. But in general, if it's verifiable, yes.
And you're not using any.
And so you volunteered to write the first VB driver, Jim?
That would be a stunt.
Yeah, sure.
So, I mean, all this, of course, begs the question, because you made the comparison with Windows, but of course on Windows I can run applications, right?
Oh, dang it, I knew we forgot something.
So let's talk about that level
Okay.
of...
Next thing you can ask about is like customers or something.
We don't go there. Well, so applications. Well, all right. So we say all the applications have to be type safe as well.
Sure.
We should talk a little bit about the status of the system.
Okay.
Because
Exactly.
I think when
Let's do that.
I'm trying to remember when out August when we. Yeah. Okay.
August. It was pretty early.
Yeah. All right. It was this summer. So we're at the point now where we have the Singularity kernel up and running, and we have a file system on top of it, and we have a network stack on top of it, and a web server on top of it. And so we've actually run, since the last time we talked with you, we've run the SpecWeb 99 benchmark on top of Singularity with some caveats. Caveats of the form of,
Well, we didn't follow all of the benchmarking rules precisely. We're sort of no different than any other academic
Yeah,
use
it's
of this
pretty-
benchmark.
sure.
We ran a shorter version of it and scaled down the data sets a little bit.
Yeah.
Our stack doesn't do the full TCP implementation like you're supposed to if you use
okay,
the
not only your
benchmarks.
hand waving, you sound like you're hand waving.
Yeah, I'm hand waving a little. I'm trying to remember all the things, but
we actually have a disclaimer in the,
We have
there's a technical report that we put out that anybody can go read, by the way.
And I've seen they've talked about it on
Yeah,
a few forums.
and we have a complete disclaimer in there of exactly the thing. But in spirit, we ran the SpecWeb.
Yeah.
Okay.
Yeah, we had the functionality of the SpecWeb
Yeah.
benchmark. There are, obviously when you do benchmarking, you have to sort of say, you have to run this test, but then you also have to impose a lot of restrictions about how you run the test to make sure that people are comparing apples to apples, not apples to oranges. In our case, we didn't sort of follow all of the rules, so it might be apples versus pineapples or something.
No, it's closer than that. No, it's like that's kind of like we kind of paired green apples and red apples. There's a couple of there are some cosmetic differences,
Okay.
but
Yeah.
but
It's probably
You
a
know,
better analogy.
but legit, there's some cosmetic differences, but we try to stay as true to the benchmark as possible, and
And so you
you can
did,
get a good feel.
so great results.
the rest.
What's going on?
So there's good news and there's bad news.
Uh-huh.
The good news is, yeah, we didn't talk about performance at all the last time when we did this. Okay, all right.
Now you've
about
got
performance.
compiler people here, you have to.
Yeah,
Yes.
okay. So we, the good news is, if you look at the round trip time to do one of these requests, these spec web requests, spec web, the way the benchmark works, there's a standard set of requests you do, and you measure like the average time for a request across some number of, and the average time is for Singularity is within 10% of Windows, and the Windows version, by the way, that we ran was using ISAPI, so it's the highly optimized version of the benchmark. It's not what you get if you just went and got the benchmark kit. It's what you would get after you tuned it extensively for maximum performance. And we get within 10% on how long.
I think we're faster in terms of we are faster in terms of latency.
Am I getting the 300?
Yeah, you got it reversed.
Oh,
so
okay.
we're about 10% faster than Windows in terms of latency, in spite of the
right.
fact that, on Singularity, we are, running this entirely in a Singularity architecture. So the extension to the our web server is running in a separate process, communicating over channels. You're talking to the TCP/IP stack, which is running its own process, which is communicating over channels. The device driver that controls the network card is also talking over channels. So, in spite of all of that, the latency is extremely good. I would say we're comparable to Windows.
You should talk about the throughput.
Okay. The throughput, unfortunately, is a little bit limited.
Yeah.
What we found is that our file system doesn't have enough throughput to support this particular benchmark, and so we're going back and fixing the file system. And we see no reason why when we get the file system's performance up that we aren't going to be comparable to Windows in that dimension either.
Now, you mentioned that's something that's very interesting. We didn't talk about last time. That's the notion of channels. Can you talk about that?
Yeah,
Sure.
We might have mentioned it briefly.
Now's a
last
good
Now's a
time
good
to
time.
talk about it.
So
That's right.
channels are one of the consequences of Singularity. So, I said we made a bunch of design decisions. One of the decisions we made very early on in Singularity is that the processes on Singularity are going to be closed. And by closed, we mean that you can bring together code from multiple places. So you can have, an exe file and some libraries that are bringing code into the process. But once the process starts executing, there's no more code that's going to be added to it. In particular, you can't do dynamic code loading, and you can't do runtime code generation. And the reason we did this is that we wanted to be able to have a closed world for each of these processes. We wanted to understand all of the code that was in the process at some point. We wanted to be able to say, this is it. Not that we think this is it, but if there's some dynamic loading that goes on, you could redefine a bunch of the libraries, you could bring in some new functions and new classes. If you do that, it's really hard to do the kind of program analysis that you need to do highly optimizing compilers, because the compiler has to make some either unsafe assumptions that it sees all the code and nothing's going to happen at runtime, even though it could happen, or you have to make very conservative assumptions the other way, which is that something bad could happen, in which case I shouldn't do this optimization. I should generate the sort of most vanilla code that checks all the time to see whether the world has changed. And we didn't want to go that way. We wanted really highly optimizing code. And the same reasoning also applies in terms of tools. So if you're going to build tools that detect errors in programs, you want to be able to be sure that you know what the code is. You have to have this closed world to be able to do really good program analysis, and we wanted to be able to do this. So, did you have something, David?
I have a few more things to say. Sure. So part of this closed process assumption, what this means is that with the closed process assumption, it means that in particular, we don't need to carry the weight of a just-in-time compiler around with us when our processes start up. So this actually has some impact on the performance of the system. This is how you can get real systems code level performance. We don't carry a JIT with us. We don't carry the ability to do the dynamic linking with us. we don't carry, so when normally it's like DLLs, for example, you do not dynamic linking and loading. In a JIT, you have this, when you load code at runtime, you're actually doing, there's a dynamic linking step where you actually link the code with everything else that exists. We don't have to do that. We don't have to keep those tables around. And because we do things ahead of time, we can spend more time optimizing the code. You know, it's not like the application is going to be held up because we decided to do this extra compiler optimization. So, in fact, we throw a whole bunch of compiler optimizations at this that are pretty sophisticated. For example, array bounds check elimination, a bunch of whole program analyses. So, for example, if you have a method that as a virtual method that you never override, well, when you got the whole program, you can tell that you never overrode this method. So you can actually turn that into a static instance call. And then once you turn it into a static instance call, you can inline it. So we can take advantage of this whole program assumption, certainly in compilation. And we can also use the fact that it's a closed process to do ahead of time compilation. And even beyond that, we can actually specialize the runtime system. So you can actually have different runtime systems for different processes because the processes themselves, I guess that gets into more of the object space assumption too. So anyway, but you guys should talk about talk about the verification stuff because that's really important.
Okay, but let me get back to the original point, which is why do we have channels? Yes. So we have these closed worlds, these processes, but you have to be able to communicate. One of the things we didn't want to do in a closed world is we didn't really want to have shared memory. So if you have two processes, one way to communicate is basically to have them share some memory and allow them to pass objects back and forth between the shared memory. There are a couple of reasons we didn't want that. One of them is that if you have two processes sharing memory and one fails, then the other one basically has to make the assumption that anything that was in the shared part of the heap is corrupted. It doesn't know what state the failed process was in when it died. And so you basically have to make a conservative assumption. Basically, in most cases, both of the processes die at that point. So that's not a great communication mechanism where sort of the failure of one process entails the failure of the other process. Another thing is that it also makes the analysis of the program a lot more difficult if you have this kind of sharing between them. And it ties the runtime systems together, particularly if they both have garbage collectors. Then you have to have coordination between the garbage collectors to see who's going to collect the shared objects. So we didn't want to go down that route, which really left us with message passing. And so what we've done is we've come up with an extremely efficient mechanism for communicating between two processes. It's called a channel. And what the channel is basically a bidirectional message passing connection between two processes. Both processes can send messages on it between each of them. And the channel comes along with a contract. And the contract specifies both the format of the messages in terms of what are the values that each message contains and the types of it. And also it specifies the legal sequences of messages between the two processes. And we check that. We literally check that at compile time to make sure that you're going to send the right message at the right time. And we give you a compile error that says, you're sending the wrong message. The channel is in the state that you shouldn't send that message. Or, you could receive a message at this point that you are not ready to handle. You forgot about this message. You should check this. And this has a lot of advantages, one of which is that the processes are very separate from each other with these channels. Is that one process dies, we can give the other process very clean notification. All of the messages that are on the channel are still on the channel. When the surviving process reads those messages and then tries to read something else, it gets a notification saying the other process is gone. You should do something because you need to clean up, you need to recover from it. It doesn't have to worry about something being corrupted at that point because it gets a very clean notification that doesn't have the sharing. Second thing is that we also have very efficient message passing. We chose a semantics for the messages, which basically says when a process sends the message, it loses ownership of the message. Literally, the ownership of the message passes to the channel, and when the other process receives it, it gets the ownership of the message. The analogy I like is when you put a letter in a mailbox, you don't have the letter anymore. If you wanted to remember what was in it, you needed to keep a copy of it before you sent it. And similarly, the post office has control of it and then delivers it to the recipient, and the post office no longer has ownership of it. And this is a really important thing for us because there are a couple consequences of it. One of which is that the sending and the receiving process can't tell how we implement the message passing. can't tell whether we copy the values between the two processes or pass a pointer to the message. And in fact, we do pass a lot of pointers around because it makes for a much more efficient way of passing data. So we literally can take data off the disk, read a block of data, and then pass that as a message up the TCP/IP stack to the application process. Oops, I meant the network.
Normally we
That's why they don't
connect.
let me write code. Because I make mistakes like that.
Well, I think we should have Manuel talk a bit about some of the static checking that he's done, as well as the exchange heap.
Right. So Jim said so of course most of the things that happen on channels. So the interesting thing is, as you said before, that is given the design that we chose, we don't want the system to be completely bad in terms of performance. And if you have a lot of processes, separate processes, that is, if you have a driver and you have the network stack and you have the application, they're all separate processes. Sure. Then you'd have to, if you get a buffer from the network, you have to copy it 3 times at least to get it up to the application, and you don't want to do that. So that's, I think, one of the main reasons why in traditional operating systems all these things are integrated down into the kernel. Is you have the driver, you have the network stack, and that's why you have the problems that, well, if something goes bad, the whole kernel goes down. Mm-hmm. And so having separate processes was really our way to make this thing more reliable from the design point of view. And then the challenge is, well, how can we still make it efficient, right? And so what Jim mentioned is that we use these channels to pass messages, in particular, like, let's say, buffers of network packets, and we still want to make sure that we don't corrupt memory, okay? And that's one of the important things. And so, in fact, this ownership transfer that Jim mentioned, that sort of gets us back to explicit memory management. So, like you have, for example, in C and C++, where you alloc memory and then you free it. And of course, there's the obvious errors that you can make. Because you can free your memory and then you still touch it or read from it, right? Which is very bad. And so, in some sense, we introduced this kind of error into our system, and we don't want to have unsafe code, as we discussed before. So what the compiler does is actually verify statically that whenever you send the message, or otherwise delete it, or otherwise lose ownership of it, you really don't touch it anymore. You don't touch that memory anymore. So we again get the compile time safety guarantee that even though we have this kind of very sophisticated way of passing ownership of memory around, you still don't lose the safety guarantee.
So now if I were a process and I send a message to another process through a channel, yes, and I wanted that message, I wanted that process to do something to that, send it back to me, how do I know it's what I sent? So you have to actually program.
So you would basically program a normal allocation of a buffer, maybe put some stuff in the buffer, send a message passing that buffer ownership to the other process. At that point, you don't own this buffer, so you can't touch it. Then later on, maybe you may receive a message, and the message carries another buffer. Maybe the same buffer, but from your perspective, it doesn't matter. You just got another buffer back, which contains hopefully the data that you wanted to contain. So it's not guaranteed that it's the same pointer at that point, but that shouldn't matter from your perspective.
Okay, so that a channel actually is a process, though, right? It has its own memory. Isn't it running?
It's not.
No.
Well,
it's not a thing. It's not a construct.
It is a construct, but it's not a process. So,
okay,
it does have its own memory. It is another abstraction that's provided by the Singularity kernel on the system. But, there isn't actually code running inside a channel. I mean, a process gives a message to the channel then delivers it to the other side, the other process on the channel. And literally, there are only 2 processes.
That's conceptual.
On a channel.
I mean, we can maybe talk a little bit about how it's implemented.
Yeah, you should talk about how it's implemented.
You should talk about the exchange heap too, because that would make it more clear
so,
what's going on here.
Maybe you want to use the whiteboard.
Well, I don't know. Well, let me try to sketch it in the air. So the.
I brought another tape, by the way, so we can always just continue this.
Oh, joy!
You don't have to better do. He just wants to see more. Sure.
No. All right. So the key aspect that Jim mentioned before is that we have these channel contracts that describe the sequences of messages that can arise on the channel, all the legal sequences. And what we do, in fact, is we restrict these sequences to state machines of the channel, so that we can restrict how many outstanding messages can be in any of the receive queues. So That allows us to then compile the two channel endpoints so that when you allocate a channel, you can allocate all the buffers you will ever need at runtime for that channel. So you don't, when you send a message, you don't have to allocate any memory to hold that message. And when you receive a message, again, there's no allocation, and you also know the allocation. And that makes it really good to implement these channels, because what you can do for a send is essentially you basically just store into the message buffers that you already pre-allocated when you created the channel. You just store the data directly in some particular place that's reserved for that time in the protocol. Okay, and so it's really, sending is really just writing some data and waking up the thread possibly. And the receiving is just checking whether data is there, which is reading memory, and then getting the data out, which is also reading memory. And that's it. So sending and receiving is very efficient in our system.
So just to be really random, why did you decide to use threads?
Within a process?
Yeah, I mean, your whole initial hypothesis was, can we make a purely efficient, safe, stable, reliable system? Yeah, you chose a construct that is perhaps...
And we chose it reluctantly. We're very much aware of the drawbacks of threads and explicit synchronization. So, one possibility was that we basically don't even allow threads inside a process. That, if you want sort of concurrency, you have multiple processes and have them communicate over channels. I couldn't get that past the operating systems guys. I would have probably been willing to try that for building a system, but it might have been a very difficult structure.
Ossified, belligerent operating systems guy said, "We're not quite sure we want to go that far yet."
Yeah. So that was one issue. And then when we actually started looking at the structure of these processes with channels, we realized we need some sort of internal concurrency. Think about a process that's handling multiple channels that has multiple outstanding requests on them. So, you're getting messages asynchronously on different channels and trying to do separate computations on each of these channels. How do you structure the code within a process to do this? There are two alternatives, one of which is obviously threads. And the other one is a single threaded model based on event handlers, let's say. So the arrival of each message on a channel is a particular event. That event invokes a handler. The handler runs a small piece of code which updates the state associated with that channel. We actually looked at this in some detail in terms of writing codes this way. When we tried writing a process this way and using threads, and what we decided is that you lose the structure of the code if you write it as a bunch of event handlers. Each handler makes sense, but you don't see the big picture. You don't see the forest for the trees. And moreover, there's a lot of experience in windowing code, for instance, that says that this is extremely difficult code for people to maintain, because the first person who wrote it may have had a clear picture in their mind, but it goes away in their mind, and the next person that comes along has no idea what it is. So, we deliberately chose threads, knowing that there's some problems with it. And I think in our context, a lot of the problems come up because of synchronization, as they do in many uses of threads. So we're actually exploring other alternatives than conventional lock-based synchronization. So there's an idea called transactional memory, where instead of using explicit mutexes or other sort of synchronization devices, if you have a piece of code that's manipulating a shared structure within inside a process in the shared memory part of the Singularity system, you say, you wrap it in a transaction. You say, begin atomic, do the manipulation, end atomic. And the system takes it upon itself to guarantee that the code within the transaction executes atomically with respect to all the other threads that are running concurrently. And atomically basically means that all the other threads either see the state change that you're making before it occurs or after. They don't see the intermediate state while you're doing the computation. So it's as if you had a lock that said, I'm the only thread that's running at this point. And moreover, we also give you some of the other guarantees of transactions that, either this transaction occurs entirely or it doesn't occur at all. So if it fails somewhere in between, it gets cleaned up and we go back to a consistent state, and we don't leave it hanging halfway in between. There are some interesting implementation issues, and there's an open question whether this is a good idea without hardware support. But we have an implementation of this, and we're looking forward to actually seeing whether we can use this effectively and whether it'll eliminate a lot of the errors that occur with explicit synchronization.
Now, you mentioned you have a rather large team. Do you have any members that are working on hardware innovations to maybe help you with this type of problem?
Not really. We've talked about it. We've certainly thought about it. But Microsoft is really a software company, not a hardware company. There's a lot of great research actually going on in this area about hardware at universities and some of the other companies as well.
So are you Mr. OS man? Are you ready to whiteboard the architecture of this book?
Sure, why not? Let's
Diagram
go
up the
white.
end after
Go
we
white.
described it.
All right.
Why not?
All right.
Let's see, do we have enough light in here?
I don't know. Do we? Do we need to go in my office?
Could we see this running, or is that not feasible?
Can you
What
see
would we
it
see?
running?
What would we be
Yeah,
looking
we
at?
could demo it.
Could you demo something without a shell?
Yeah, you can. Well, we have a printer shell. Yeah, we have a demo. Yeah.
Cool.
Yeah, it does look like DOS. We'll have to pause the video for a minute while I just
Certainly.
make sure it
We can
works.
totally do that. But
Okay.
do we want to? Do you think it's worthwhile to whiteboard this stuff up now that we've explained it?
It might be good to give people a picture
The
to hang all these
Sure.
pieces on.
Yeah.
Yeah,
Okay.
that'd be nice.
All right.
Do you want to
All
go
right,
in your
so-
office? Because I don't really have enough light in here.
Okay. Well,
Let's walk into the lighted room.
all right. Let's go into Galen's office. Oh, quick! Galen, erase the whiteboard.
Sure. I'm going to pause this real quick.
Okay, so Singularity is a class of system we call microkernel. All right. So at the bottom, let's try black. Okay. So at the bottom of the system, we have a microkernel. And the microkernel, the Singularity microkernel has things. There's a scheduler in here. The scheduler schedules threads. There's a channel manager that sets up communication. There's a security manager. There's an I/O subsystem, an I/O manager that's responsible for device drivers and starting and stopping them and enumerating hardware. I'm sure I'm forgetting something. There's this thing that we call the hardware abstraction layer, the HAL.
We've heard that.
Okay,
before.
you've heard of that before. And in Singularity, the HAL contains, there's the timer, there's the programmable interrupt controller, and then there is also the real-time clock. Okay, this is actually the hardware that's known about by the kernel, and I guess sort of related to this. There's the virtual memory unit, the virtual memory
You
manager.
need to add to scheduler channel security. You need to add memory management.
Ah, yes.
You need to actually give memory.
Yes, yeah, we actually have a memory manager. Okay, the page manager is what we call it, but I'll leave it as memory manager here.
Now, all of these components are written in C#, spec sharp, except for the obvious ones that maybe
okay,
HAL.
so the I/O manager is written almost entirely in spec sharp.
Fantastic.
Security is as well.
The memory manager is written in C# with a lot of unsafe C# in it. It's one of the places where we have the most amount of unsafe code. Most of the rest of the system is C# or Sing
All the memory
sharp.
manager does is give you pages of memory. So you hand it pages of memory, and it takes pages of memory, and you can give them back to it, or it reclaims them when the process ends. So even though the memory manager, even though Galen says it has tons of unsafe code, it's fairly simple stuff.
Yeah, sure.
Okay.
It's
Just basic operating system stuff.
Yeah, it's very analogous to say code that you'd see in a regular operating system for memory management and memory allocation. It has a list of free pages and things like that. Okay. Anyway, the point I want to make about this HAL right here is that this is the only hardware that the kernel knows about. Okay. Or that the kernel specifically manages, and it has to own these so that it can do scheduling, it can control scheduling and give time to everybody else. And then everything else sits up in processes, okay? So, or as we call them, SIPs, software isolated processes. So for example, the web demo, for example, the spec web demo. So there's a process that has the NIC in, okay, device driver. And there's another process that has the disk device driver in it. And there's another process that has the TCP/IP stack. And there's another process that has the file system. And then there's another process that has the web server. okay, which is the Cassini web server. Okay, so this is, people may have heard of Cassini if they've ever heard of Rotor. I don't know if you've done an interview with the Rotor people
Not
before.
yet.
Okay, it's a useful one to go do. And then, so all the applications run in processors, in SIPs. And then extensions to applications run in SIPs as well, because remember we have closed processes. So the dynamic content generator for Spec Web runs in its own process over here. Okay, and then all of these communicate using. Let's see, we definitely wouldn't want to do communication that way right there. So like from the NIC to the TCP to the web server to the dynamic content generator, that's all through channels.
Channels.
Okay.
Okay.
And I don't think you didn't talk about the exchange.
We need to,
No,
I
not
kept
yet.
saying, we need to talk about the exchange heap.
Okay, so there's one other special piece of memory in the system, okay? And we call this the EX heap, the exchange heap, okay? And these channels, I've drawn them abstractly as these lines up here. Well, what they really are is a channel is some memory down here in this exchangeable heap because it has to be visible to two processes, okay? All this other memory, all the memory up here in the process, in the SIPs, the kernel memory, each of these is visible only to that particular piece of the system. Okay, so for example, in a process, okay, let's go over here to the NIC process, for example. So the NIC has its own garbage collector in here, okay? The runtime and its own runtime. Each process has its own runtime and its own garbage collector, okay? And it's a set of pages that are owned specifically by that SIP, okay? And the guarantee is that this SIP, all of the references and the object references and pointers stay within that SIP, okay? And so if you want to communicate, when you actually, and this is done by the kernel when it creates a channel, well, it's allocated in this area called the exchange heap. And so that the two, so let's see, what I've done is I've drawn the channel here between the Spec Web server and the Spec Web content and the web server. And each of them, there's two halves of the channel called endpoints, one endpoint for each process, or for each end of the channel.
Sure.
Okay. And then the other thing that goes in the exchange heap is, let's say you have a block that's coming in off the disk, okay? That you want to be able to take this big buffer and move it between processes. Well, that gets allocated in the exchangeable heap, and then the disk owns it. And then when the disk puts it in a channel that goes to the file system, then the disk loses its pointer to that object, or that data structure. It's not an object, it's a data structure, and the file system gets it. Okay. And so these large bulk data transfers go through this exchange heap, but we still maintain these two invariants, which are no process ever contains a pointer to another process. Okay. And the exchange heap never contains a pointer to any process. Okay. And then a given piece in the exchange heap can only be pointed to by one process.
So you probably just explained this, but I'm going to ask you
Okay,
anyway.
please do.
I used to always do that in my math classes. So if each process has its own garbage collector, what's to prevent another garbage collector from overwriting someone else's memory or deciding to take it? So what I mean by that, where is each garbage collector's memory allocated? What allocates that?
Well, so that's down here, this page manager, right? I wrote it as memory manager. Let's fix it.
Page manager.
Yeah, okay. So
All
this is the page manager, okay? And what happens is the garbage collector makes a kernel call down to the page manager and says,
Give me some memory.
Can I have some memory?
Got it.
Okay. And now it owns that memory and it plays with it. Okay. And when it's all done, say it does a garbage collect and decides we don't need as much memory anymore, it calls the page manager back and says, here, you can take this memory.
Understood.
So you need to draw the picture of what's trusted and what's not trusted here. Okay.
Colors.
Colors.
Great.
Well,
Okay.
no,
All right.
it's key.
Okay.
You asked the question, what prevents the GC from actually sort
okay.
of walking over somebody else's
All right.
memory?
So can you see the red?
It's blue.
The red, the blue? Yeah, the blue. Yeah, sorry. No, and I'm not colorblind, believe it or not. I just can't speak. Okay, so this green, okay, the runtime and the garbage collector are trusted, okay? Likewise, as with, okay, we're getting too much black. Likewise, the kernel is trusted as well, okay? In a traditional system, the kernel's always trusted, okay? Well, the way to think about, there's at least a subset of this runtime called the trusted runtime that includes the garbage collector, and it is trusted. It's a trusted part of the system, okay? And you could almost think of it as it is a piece of the kernel that we run in each process, okay? From a kind of a trusted computing-based security model, you really want to think of it as there's some piece of our kernel that we get to run in everybody's process, okay? This is one of the things that I always get really excited about, is that we can do this. We can run this trusted code there because of the type safety. Because we verified all of the other code around in this process, we know that it can't somehow subvert this trusted runtime, okay, because it's protected by type safety. And so we actually can trust it. So one of the examples of this that I'll hit on really quick is, okay, you've got this NIC, all right? The NIC has to be able to talk to hardware, okay?
Sure.
And Jim already talked about how there's some objects that we encapsulate in an object, the unsafe code for accessing hardware in a safe object. Well, that safe object gets created by the runtime in the SIP and then passed up to the rest of the NIC code. So it's got this safe object that it talks to, that the safe runtime created for it, and then it can talk to that. And so the NIC doesn't know how to create an object talk to any other piece of hardware because the safe runtime, in cooperation with the kernel, decided that this process could get an object to talk to a piece of the NIC because it is in fact the NIC device driver. So it wouldn't give that same object to the disk driver.
Fantastic.
A bit of it is something.
That's great.
I'm a sys guy. I'm an OS guy.
It fits in nicely with the whole.
And from the safety perspective, the nice thing is that we can do bounds checking on this thing, for example.
Yes.
If you're storing bytes into an individual buffer, we can do bounds checking. And if a compiler is really clever, and in some cases we are clever enough to do this, we can eliminate some of the bounds checking on the stores into this memory. And so when we say safe, we really mean safe. I mean, everything has bounds checking, for example, that's running in the user process. And the bounds checking is only eliminated if the compiler can prove that you don't need it. And so that's very cool. From a compiler perspective, this is really cool because now part of the kernel is running in our space, and the optimizer can actually start to do fun things.
Yeah,
like this.
it's really cool. The optimizer can optimize this code, and hoist it up into the application, the rest of the application code. But we know it's safe.
So we can actually inline parts of this code in, and it's safe.
So the notion of kernel mode, user mode is a little blurred. What would shell look like in this picture?
So actually, no.
No.
Okay. The notion of kernel mode, user mode is actually, while we don't depend on hardware to maintain it, there's a very solid boundary right here. Okay. And I always use the term, and everybody has no clue what I'm talking about. I say the application binary interface. If you have any viewers that were around in 1980s doing Unix programming, they probably know what they have heard of the term at least and forgotten. But there's a very hard boundary here about qualities that are maintained. So, for example, one of the qualities we maintain is that we'll never pass an object across this boundary. From a process into the kernel, or from the kernel into the process. The kernel's got its own garbage collector. It's its own garbage collection domain. Okay. And so we don't want objects to leak across this boundary, and we actually can statically check that. It's one of the things beyond type safety to check. Okay. And so there's a very hard there's a very discrete, sharp boundary that's checked. Doesn't rely on hardware, but oh man, I've lost my place. Lost my place. But so this code up here,
I just want to say one thing. I'm running out of this tape. Yeah. So can I change the tape?
Or maybe we should.
Can we do this some other time?
Yeah. We should call this one session. I think we've pretty well covered the architecture.
I think we're in a pretty good breaking point.
Maybe we can come back sometime and talk about some of the other aspects of the system as well.
I really would like to do that. So we'll do a Singularity 3.
Great.
Okay. So thank you very much for your time. I know you guys are really, really busy. And this is great work. Very interesting stuff.
Thanks.
Thank you very much. Thanks.
It was great doing the first one.
Great. Take care.